Hi, let's see what I can do with problem 13. We have L squared q points of order L, so let the generators be ui we have a point, or maybe I should speak why we have two generators. If there's only one generator, ui, so ui to the lth is unity. That gives L points, so there need to be another. And could they come from the same generator? Not without hitting the same family. All right. Now, we have an FQ point, A, and an extension that contains an alpha, so L alpha equals A. Show there are L squared points. The points of order L I u1 plus j u2 L minus 1. There we go. So that's the L square generators. Let's call them omega ij. I claim that alpha ij A, if we take L to them, then we get alpha. If we multiply them by L, and that must be added. That equals L alpha ij plus L alpha equals unit element plus A equals A. So these are the L squared solutions to this equation. Right. And there can't possibly be more, because if we have two, then the difference we already have this, I think. That means that L alpha minus beta is the unit element, which in turn means that it's one of these L squared points. All right, that's A. B. Now we have a point that maps to A, and A is an FQ point. Prove that the map gives an embedding into the group. Embedding into which group? Into the points of order L. So obviously these have order L, or do they not? Yes, they do. It was kind of obvious to me, but for some reason I needed to perform this calculation. So it maps into the points of order L. And then we have to show that it's an embedding, meaning it's one-to-one, or injective, an injection. And so that's 1, 2, and then we must prove that sigma is the constant. Not constant, the identity. Sorry. This means that sigma of L alpha, not L, or that too, but I meant I alpha equals I alpha. So all the powers of alpha, it's constant on all of them, but we need to show that it also holds for the other. Well, we already know that they come like this, so the others have the form and now we just call it, well, let's call it Uij. And then we operate with sigma on that. Sigma alpha was alpha, and this is the unit. It's constant on FQ, so this is equal to Uij, and that was exactly beta. So it's constant on all the elements alpha. And that means it is the identity. So we need to show that these points actually generate FQ to R. Oh no, that's not necessary. Oh yes. So the minimal extension containing these points is Galois over FQ, and it's an finite extension, so it is one of these, and since it's the minimal, then if if sigma is constant on all of them, they will generate a subfield. And since it's the minimal field already, then sigma must be constant, the identity operator or automorphism. That was B. Show that R is either 1 or L. It's 1 if they already lie in FQ. If they lie in an extension, then that extension is interesting, because we have L square points. You see, I thought there would be an automorphism mapping each of these guys or one of the, say, alpha to each of these guys, so that the Galois group was transitive. And since there are L squared of these guys, I thought that the Galois group would have order L squared. I'll have to study what is the condition that the Galois group is transitive. I don't know what that is, and I need to find it out before I continue. All right, that turned out to be a misunderstanding. The automorphisms act transitively on the roots of the polynomial of the extension, not the points of the elliptic curve. And I don't know how to get further than that there are at most L squared automorphisms. It's time for my lunch break, and then I'll continue afterwards. I have had my lunch now, and I think I have an idea. If we have to prove that sigma has order at most L, let's try to compute sigma squared. So we write sigma of alpha equals alpha plus an element of order L, which depends upon sigma, doesn't it? Yes, definitely. It's unique for sigma. Now, to find the order, let's try to compute sigma squared. Oops. Do it very thoroughly. Sigma alpha is alpha plus 2 ui plus u ui Now we can make an induction proving that sigma to the ith of alpha equals alpha plus I, that was poor choice, k times uik. And if k gets sufficiently large, like L, then this is the unit element. So to prove C, let sigma be an element of maximal order. Then this holds, and that means that sigma to the Lth is the identity map, meaning that sigma has order L. So that proves that it has order L or unity. Now D, the extension field generated by all the points This reminds me of problem part D of the last problem, because it's FQ to L in naught, FQ to L to the first, FQ to L to the second, etc. And I believe that I described the Galois groups in connection in the last problem. So if we have F Q L to N over FQ, oops. Oh yeah, the Galois group of the then I believe it has the form. First we start with the Frobenius automorphism, and then we define the automorphism by the Frobenius in F, where Q equals P to F's. And then the automorphisms are given by powers of H, where I goes from naught to, and then we need to find out the order of that guy. This is L to naught, so it's the L to N. Yeah, what is it now? Yeah, L to nth minus 1. So I believe this is the Galois group. Oh, that was the first chapter. I have displayed my grid, have I not?